Mhm. Mhm.
Okay, good evening, everyone. Thank you for joining for the second RASP session. Today we have Dr. Rajaram with Nityananda, who will be handling the session. So Dr. Rajaram has worked in areas of physics and astronomy at the Raman Research Institute for more than 2 decades and at the National Center of Radio Astrophysics for Tata Institute of Fundamental Research for a decade. He has taught at IISER Pune and most recently at Azim Premji University. He writes for a college student audience in Resonance, Journal of Science Education. We are glad to have you here, sir. Thank you.
Hello, everyone. Really nice to have such an enthusiastic audience, which I saw yesterday, asking questions, taking part. I hope that will continue. Thanks also to Nakshatra for setting this up. So let's begin. Let me start by sharing screen. Yeah. So I'm more used to teaching with a blackboard, but in this online format, this is the best I could do. So do tell me if things are legible and so on, right? And if also my voice is audible, that can happen in an online setting. Okay. As far as putting up your hands is concerned, since I'm not looking at all the participants' images all the time, I request one of the Nakshatra team, Sagar or one of the others, to interrupt and say, okay, so-and-so has a question, right?
Sure, sir. And moreover, we can have breaks here and there, and during the breaks, we can address those questions.
Okay. That's nice. Yeah, I should do that. So what you've heard from my friend and longtime colleague, Dwarkanath, is about all the kinds of different objects in the universe which radio waves has contributed to understanding. And of course, he told you much more about specific objects. Now, I'm going to get a little bit into the physics of how these radio waves are produced. And to start with, let's even talk of units. Let's get the units straight, right? So suppose, let's say one is looking at the sun, need not even be radio waves, could be visible light, and someone tells you, look, I have collected 10 joules of energy from the sun. Now that's meaningless, right? How long did that person collect? Over what area did that person collect? And also, whenever you observe, your instrument will always admit a certain range of wavelengths or a certain range of frequencies, right? So the more meaningful quantity to describe what you receive from any astronomical source is something called, this is the symbol, and it goes by the name of flux density. Yeah. So the definition is very simple. It's the amount of energy you receive, but per unit area. So it becomes watts per meter square after you make it per unit time, right? Joules per, this thing is watts per meter square per. And then, importantly, per frequency interval, and frequencies are measured in hertz. Okay. So you can make a kind of calculation. So you could do this for the sun in the visible region of the spectrum, for example. I won't do it, but I may give you people a small worksheet where you have little problems that you can work out and put in numbers. I think putting in numbers is important. Formulae are not just meant to be admired. So I did the calculation for myself, and if I remember right, the number was approximately, so let me say F nu for the sun in the visible region of the spectrum, right? So let us say between 600 nanometers and 300 nanometers, right? Something like that. So of course you have to convert that to frequency, right? So anyway, just for your reference, 600 nanometers wavelength corresponds to 5 times 10 to the 14 hertz frequency. If you don't believe me, you multiply these two numbers and you will get 3 times 10 to the 8, the speed of light. Okay. So this comes out to be something of the order of 10 to the minus 12 watts per meter square. You may see it looks very small, right? But the reason is because per hertz. Okay? By the time you multiply by 10 to the 14, you get a much more respectable number, right? Per hertz. Now, the same definition works in radio waves, but radio waves are much weaker, okay, than the sun. So, conveniently, the unit used by radio waves is called 1 Jansky. Jansky is the name of the electrical engineer, not particularly an astronomer, who detected radio waves from the Milky Way. Okay, and you can look him up. Nowadays, I don't have to give you any references. All you have to do is to Google or Wikipedia and learn all about this interesting man and his pioneering work. So in his honor, the unit which is chosen is 10 raised to minus 26 watts per meter square per hertz. Okay. And by the way, radio astronomers think of 1 Jansky as a very strong radio source. Okay. So that's, so of course, optical astronomers would not use Jansky. If they used it, they would say that this is something like 10 raised to 14 Jansky or something like that. But they use their own units, right? Magnitudes and so on. Okay. Now, just to get a feel for other uses of the radio spectrum, let's just think of a mobile phone, right? Typically, your mobile phone emits 1 watt, okay? Right? And well, what bandwidth you're using depends on exactly what you're doing. Are you doing an ordinary voice call, voice over internet, video call? So I think the video calls, I mean, I'm giving you a very rough number, might take up something like 1 megahertz, okay? Which is the same as 10 raised to 6 hertz, all right? And now this has to be picked up by the mobile tower, right? And at least in a rural area, the mobile tower might be 1 kilometer away. So remember, this is just watts. This is sent out, let us say, in all directions. So you have your cell phone, right? And it's the mobile tower is 1 kilometer away, right? So you really have to distribute this over the area of a sphere of radius 1 kilometer, right? So, so what does that become? You have this 1 watt divided by 4 pi into 1000 squared, right? So now this is watts per square meter received at the cell tower. And remember, of course, the cell tower has to pick it up and then send it somewhere else and finally to the person you're calling, right? And we also said per hertz, right? So you have a factor of 1 million here and you again have another factor of 1 million here, right? And this is roughly 10, right? So you've already got to 10 minus 13. But notice, this is still a huge number compared to our radio astronomy unit of 10 minus 26, right? So this 10 minus 13 is 10 raised to 13 Jansky. So just to give you a feel for what this 1 Jansky is, instead of having the mobile phone 1 kilometer away from you, suppose the mobile phone was placed on the moon, right? Now that's 4 times 10 to the 5 kilometers is the distance from the Earth to the moon, right? So then what would we get? We have to, instead of putting 1000 squared, 1 kilometer squared, we have to have 4 times 10 to the 5 squared in the denominator, right? So that would knock off another 10 powers. You'd still be at thousands of Jansky. Now this tells you a very fundamental fact about radio astronomy. Now, Mr. Jansky worked for Bell Telephone Company, pioneering telecommunications engineer. A lot of the technology in radio astronomy, which you will learn from my colleague Ramesh, right, is developed for telecommunication, right? But the irony is that radio astronomers love telecommunications equipment and techniques, but they're not very happy with telecommunication because a small mobile phone can produce a signal far greater than what you receive from an astronomical source. So this is a major problem at all observatories. And I hope this also gives you a feel for the various units that we are talking about. Now, I just want to make one more point. Jansky is fine as a unit for what you measure at the Earth. Okay. And so this already corrects for the area of your instrument and your observing bandwidth and all that. What it does not correct for is the distance of the source. So this is still not a source property, right? The same source, if you put it at greater and greater distances, like we did for our mobile phone, will give you a smaller and smaller flux density. So you might be interested from the point of view of astronomy in what we call luminosity of the source, L nu. Yes, I mean, it's called luminosity. So that's the total energy put out by that source in all directions, like this 1 watt for a mobile phone, right? So how do you get this? You take the flux density which you receive at Earth, and then you multiply. So you see that one of the most important and also one of the most difficult things in astronomy is to measure distances, right? You can't really find out a property of the source. So whenever new sources are discovered in radio astronomy, and before they know the distance, you will have all kinds of theories. Okay, maybe it is something in our solar system. Maybe it is something in our galaxy. Maybe it is something in remote galaxies. And depending on what distance you put it, you will increase your estimate of the luminosity of the source. You'll be talking of more and more energetic events. Huh? So that's a simple thing to keep in mind. Okay. So now I'm going to tell you about yet another quantity which is measured in radio astronomy, which has the advantage of being independent of distance. Okay. So I'd like to introduce that concept. I'm going to be very liberal with these boards. I'm going to store them, even though it'll take a little time, right? So let me see, save as. Okay. No, I don't want to save it as Einstein argument, right? That's somewhere else. Yeah. So we will just call this. And we can also use these breaks for you to think about what I have put down on the board. And yeah. So now we can clear the board. And okay, that nice color went away, of course, but I think I can probably bring it back. But why should everything be the same color, right? So right. So now the quantity I'm going to talk about, and I'll need a different color for this. Is called specific intensity. That's the name. The symbol is I nu, and it's actually very simply related to F nu. Okay, but with a very important added thing, is equal to F nu divided by the solid angle. Now, a quick reminder of what solid angle is. Your ordinary angle measured in radians is nothing but this arc length divided by the radius, right? Theta is equal to arc length divided by the radius, right? And solid angle, similarly, is if you are sitting at some point and observing all directions within some cone, let us say. It doesn't have to be a perfect cone. No, this is like a solid angle. For example, this could be a cone of radius 1 degree or something like that. Except that the unit that people like is you draw a sphere around this point and let this cone intercept the sphere in some area A, right? So A divided by R squared is the solid angle. So the first thing you can see is the total solid angle going everywhere is 4 pi, just like the total angle is 2 pi. Okay, and this unit is called steradian. I mean, so now when you saw all these beautiful pictures in the previous lecture, they were really maps, right? Maps of the sky. So then at any point, if you wanted to know how much energy you're receiving from that point, actually from a single point, you're receiving nothing, right? You have to think of a finite small patch of the sky and ask how much you're receiving from that. And that will be proportional to the solid angle for a small patch, right? So suppose you have some galaxy. Right? You might put this patch here, you might put this patch here, you might put this patch here. And you will get a different value of I nu for that. This is the technically correct name for I nu. It's a function of frequency, right? And that's why it's called I nu. It's also a function of position, right? And that's exactly what you call your picture of the sky. So you could really say that what radio astronomers or maybe other astronomers are doing when they measure I nu, right? They are measuring it. Well, I've already put the nu here. If that had not been there, I would have said they are measuring it as a function of frequency. They are measuring it as a function of direction in the sky. Now, direction, it's actually convenient to take this sphere as a unit sphere. Then you don't have to worry about this R squared, right? So you think of a unit vector which points in the direction. So this is for a fixed frequency, right? This can be plotted as a function of n hat, and that is exactly what is called a radio map. Okay. Now, of course, one must remember that I nu is defined per unit solid angle, but that doesn't mean that you have to average over one steradian, right? Any more than if you say a car is going at 100 kilometers per hour, you don't have to study it for 1 hour. You can study it for 1 second and you can convert. Right? So your map will depend on how good your instrument is. Any instrument will not measure I nu at a point. It will measure some average of that I nu over what we call the resolution of the instrument, right? So just like I told you, any instrument measuring the dependence on frequency will take in some finite frequency, right? So really, this quantity, if multiplied by the frequency range, multiplied by the solid angle, and multiplied by the area which you're collecting, right? This would be in watts. And of course, if you further multiply it by the time, this would finally be energy, just energy. So this is just a useful definition. But what I want to point out, and that's the really important property of this I nu, is so let's imagine we are observing in some cone, and let's say we are observing the sun. Okay? And it's very important that this cone is smaller than the sun, right? So the sun, many of you may know, the size of the sun in angular units is, we usually remember it as half a degree, but we should probably think of it as 1 over 120 radians. And of course, it's a circle, but if you don't mind my approximating by a square, I would say the solid angle made by the sun is approximately 10 to the minus 4 steradian. You are just squaring it to get the area. Okay. So now suppose I push the sun further away. Okay, sun has gone. Now the total energy you receive from the sun, we already saw, will fall off as 1 by r squared. However, please look, if you're looking at this cone, the cone now intercepts a bigger area of the sun, right? If I move the sun from one value of r to another value of r, it intercepts a bigger area. Right? So on the one hand, from each little piece of the sun, the energy which you receive falls off as 1 by r squared. We have already seen that. But the amount of the sun that you're looking at increases proportional to r squared. Just this little bit of geometry. Right? So the net result is these two cancel. So I knew so long as your beam, the solid angle into which your instrument looks, is smaller than the region of interest, yeah, the object you're looking at. Now the jargon for that is that the object is resolved by the telescope. So if the object is resolved, if you measure the total energy from the object, it will fall off with distance. But this quantity I knew is actually independent of distance. One term for it is specific intensity, the technically correct term. Sometimes people just call it brightness. Now, since I've given you a somewhat mathematical discussion of this, let me also tell you that we actually encounter this in daily life, if you think about it a little bit. So imagine that you're in some room and there's a completely white wall, nothing, no features on it whatsoever. And then you sit somewhere and you just look at the wall. And maybe you deliberately don't look at anything else in the room. So maybe you roll up a piece of paper into a tube and you look at the wall. Then if you walk forwards and backwards, you will not be able to tell what the distance of the wall is. So if you don't believe me, you will try it out. Of course, it will not work perfectly because any wall will have small imperfections. And as you move back and forth, those imperfections will get smaller and bigger. But for a truly uniform distribution, this quantity, which we call brightness or specific intensity, is actually independent of distance. Okay. I think I should. So I'm going to use these pauses when I store this file to give you people a chance. Right. So let's save as. And I'm doing this so that in case you have questions at the end, you can go back to the right.
Right. So we have like 3 questions. Can we address them
great,
now?
Great.
Okay. Shashwat is asking, sir, by small patches in the sky, you mean we have to then look for the point sources and from that describe the intensity?
A good question, actually. See, for a point source, we don't even know what the solid angle is, right? See, when you say point source, no real object is a point, not even a black hole, okay? Even a black hole has some size, okay? So what you mean by a point source is a source where you are unable to distinguish it from a point source, which means the source is smaller than the resolving power of your telescope. So if you have such a source, you cannot calculate I nu. What you can, of course, give is a lower limit to I nu, saying the source is not bigger than the solid angle of my beam, and therefore the specific intensity must be greater than such and such. In that case, you only measure the flux. So in the early days of radio astronomy, people would make catalogs saying, here's this point source, here's that point source, this is 1 Jansky, this is 3.4 Jansky, so on and so forth. Then when radio astronomy improved and people started making maps, those beautiful pictures which you saw yesterday, then people could talk of specific intensity. I hope that answers the question. And I'd like to take the other ones as well.
Yes, sir. So the other question by Yuvraj is, sir, n cap is direction vector in our coordinates, right?
Yes. So direction vector from the observer, toward the
Okay,
source.
according to the observer.
Toward the source.
Okay, we have Lakshmi Raja wants to unmute. Yeah, Lakshmi Raja, you can ask.
Okay. Sir, could you just explain again the concept which you explained about the sun moving back, and also how the intensity, I mean, the specific intensity became independent of the distance?
Okay. So I think unfortunately I may just end up repeating, but can you see my cursor?
Yeah,
so
yes.
Here is the observer. Here is some cone. And it's important that the size of this cone is much less than half a degree. So you're just looking at a small piece of the sun. Now, depending on the distance of the sun, the actual area of the sun which is contributing to your received signal is going to increase. Would you agree with that? That's what this picture shows.
Yeah, yes, sir.
And the area will increase proportional to r squared. Because look at the definition of solid angle. Delta omega is constant. That's the beam of your telescope. So A is proportional to solid angle into r squared. So you have two compensating factors. Every point on the sun, if you just think of it as a point source, what you receive will be inversely proportional to r squared. That's the famous inverse square law, which we already saw. Right?
Yeah,
right,
yes, sir.
Lakshmi? But
yes, sir.
The number of points contributing to you is increasing proportional to r squared. So the two cancel. I'm sorry, I just said that in words. I could have written down. And yeah. No, I think this concept is really important because I knew is actually a property of the source. So this is why people could infer the temperature of the sun without actually knowing the distance to the sun. They could measure the specific intensity coming from a small area of the sun, right? And then compare it to the specific intensity of various objects in the laboratory at different temperatures. I mean, that is the black body radiation, which was referred to by Dwarka, right? So I hope that's fine. And was there one more?
Yeah, no, sir.
Yes,
I
sir.
got that.
Okay. Okay, great. So
The question is, why do we use different units for flux in radio astronomy?
See, I think units are generally picked, right? I mean, people don't normally express the size of a cell in meters, right? They express it in micrometers. So I think depending on the field, people will choose units so that the numbers come out reasonable. So if they had used the standard SI unit, which is watts per meter square per hertz, and so on, then people would have only got numbers like 10 to the minus 26 and so on. Whereas it's much nicer to say that, yeah, today I observed one Jansky source, right? So it's just a matter of convenience.
Okay, sir. Yeah,
Nothing fundamental.
we can continue.
Yeah. Okay. Window. So what am I supposed to do? I'm supposed to edit. Clear. Yeah. So anyway, for a change, let's have a whiteboard. I hope my pen works. So now I'm going to tell you something about specific intensity. Now that it's the property of the source, we would like to understand a little more about what properties of the source influence I. Okay? So I will have what I would call a very simple model for the production of radiation from the source. Okay. So the model is this. We have a slab. For convenience, we'll call this x equal to 0. We'll call this x equal to L. And whenever you have an x, you will also have a dx. So somewhere in the middle of the slab, we have a layer of thickness, dx. Okay. Now, this slab contains some material, and you already saw that there are very, very different kinds of radiation mechanisms in astronomy. Thermal, non-thermal, synchrotron. I mean, I think they were all mentioned in passing yesterday. Now, let's just imagine, see, this need not be, this could be the surface of a star, for example, the atmosphere of a star. In that case, the lower part of the star will be feeding some radiation into the atmosphere. Or it could be a gas cloud in interstellar space. And then you might be looking at some source through the gas cloud. So just to keep the discussion general, we will say that the specific intensity entering this cloud is some I0. It is a function of frequency, but I'll omit that for a moment. Now, each slab does two things. There happen to be some sources of radiation in the slab, so they will add to this I0. Okay, so we'll have an equation di is equal to some epsilon into dx. The letter epsilon has been chosen to remind you, at least the corresponding English letter is E for emission. Okay, so this is just a proportionality of I, and it's reasonable that the amount of contribution to I will be proportional to the distance traveled. Okay, and I'm going to treat epsilon as a constant. That's why I call this a very simple model. In a real solar atmosphere, all the properties will vary with height and so on. But let's walk before we run. Okay. The second thing that the real does is it absorbs. Now, what do you mean by absorption? It means that a certain fraction of the intensity, di over I, right? And absorption means that there's a minus sign, di is negative, right? And the fraction is proportional to dx, right? So you have alpha times dx. Okay. And again, the Greek letter alpha is chosen as a placeholder for the English letter A, which is for absorption. Okay. Now, so as this radiation passes through, it's absorbed, extra radiation is added, that radiation in turn is absorbed, and so on. So sounds very complicated, right? But actually, since we have the benefit of calculus, we can do it quite easily. I don't really believe in lots of derivations in a lecture of this kind, introductory lecture, but this one is so simple that we'll do it, and it's a good investment. We'll learn a lot from it. So di over dx is going to be what? Is going to be minus alpha times I, right? That's the contribution from this term. And the contribution of this term is very simple. It's just epsilon. Now, astronomers, not just radio astronomers, but all other astronomers as well, have decided that, look, the real important combination is alpha times dx. If I have a material which is less absorbing, but I take double the thickness, the net effect will be the same. So they now make this nice definition that alpha times dx, and this is dimensionless. Huh? That's the other thing to do, because it's a fraction of radiation removed, di over I. Huh? So alpha times dx is dimensionless, whereas alpha itself has dimensions of inverse length. So alpha dx. So I'm putting these three lines to tell you that this is just a definition, nothing to be scared of. It's called d tau. So tau is dimensionless and it has a name. And this, if you move amongst astronomers, you cannot avoid this name. I wouldn't be surprised if you heard it. So this is called optical depth. So suppose we had only this equation, pure absorption. That's an even easier equation to solve, right? Logarithm of I is minus d tau. So for pure absorption, I is nothing but I naught e to the minus tau. We know how to solve this equation, right? So the meaning of optical depth is that if tau is 1, the radiation is cut down purely due to absorption by a factor of 1 over E, which is around 36 or 37%. So optical depth 1 already means there's quite a bit of absorption. However, of course, there's also emission. So this is the equation we really want to solve. And we divide by alpha so that it now looks like di by d tau, right? So now this term simply becomes minus I, make life simple. Of course, this term becomes epsilon over alpha. So it becomes minus I minus epsilon over. Now, I mean, you learn all kinds of nice techniques to solve such differential equations. But in this case, we don't need any fancy technique, because this epsilon over alpha in our very simple model is a constant, right? Epsilon is something to do with the emission properties of the medium. Alpha is something to do with the absorption properties of the medium. So this is just a constant, I minus epsilon by alpha. So what we can actually do a little bit of cheating. Maybe I'll do that. I can equally well say this is, sorry, I should have put the bracket here. I could say this is d of I minus epsilon by alpha, right? Anyway, differentiating this constant doesn't do anything. So now this is as simple as our earlier differential, right? So the solution is I minus epsilon by alpha is whatever the initial value was of I naught minus epsilon by alpha into e to the minus tau. That's it. So we've got our mathematical solution, but we have to interpret it physically, of course. And this is so simple that I don't think we need to preserve it for the future. But let's try and understand this equation. So this feels just like rubbing out the board in my classroom. So I like it. So let's write this out. I is equal to I naught e raised to minus tau. That's this term. And then you have, this is an interesting term, epsilon by alpha. When this comes with a 1, when it goes to the other side. So 1 minus e raised to minus tau. So this is the equation which every astronomer is supposed to remember. Okay. And this is the kind of obvious part, right? You have I naught sitting behind a slab of optical depth tau. And the definition of optical depth tells us that it will get attenuated by e raised to minus tau. But this is the part which is due to emission. Now, why does it have this slightly more complicated form? The reason is emission is not occurring at one place. Emission is occurring at various places. So, by the way, you could also derive this form. I'll maybe give it to you as a small problem, not by solving the differential equation, but by taking what is emitted from each layer, putting not the full tau, but the smaller value of tau from that layer to the front, putting e raised to minus that and integrating. You could do that. But this is equally. Now, we can actually understand this equation better. So this term, as I said, we understand. I'm not going to talk about it more. It's simple absorption of a background source by our slab. Now this term, let's discuss it in two limits. Let's discuss it in the limit tau far less than 1. So again, the astronomer's jargon for this is optically thin. So under those conditions, you know very well 1 minus e raised to minus tau is nothing but tau, right? It's 1 minus tau for tau less than 1. So now you have epsilon d tau by alpha. Now I'm going to go backwards and remind you of the definition of d tau, which was alpha dx, right? So this simply becomes epsilon dx. So we have just rediscovered. No, why did I say d tau? I should not have said d tau. Epsilon into tau. Tau is small, of course, but it's yeah. Yeah. So it's epsilon into L, right? Because tau is nothing but alpha into L, the full. So this is just telling you that if there's not much absorption, whatever is emitted in this region simply reaches you, right? Epsilon is the emission per unit distance, right? And you get epsilon into L. So this is the optically thin case. Now let's do the case which is called optically thick. So then you neglect this term, right? And as I said, this term is something separate, which we'll not worry about. So then we get the result I is equal to epsilon divided by alpha. Now notice something very interesting, right? If it is optically thick, The answer doesn't contain L. Right? The reason is, but I can still think of this in the following way. I can think of it as epsilon into 1 over alpha. Now, what is 1 over alpha? 1 over alpha, first of all, remember the dimensions of alpha. Alpha is length inverse. So 1 over alpha is the dimensions of length. And it also has a physical meaning. If you have a length of 1 over alpha, the optical depth is 1, right? So now I'm going to erase this equation and tell you that which is effectively equal to, so you compare to the previous formula, epsilon times L. This looks like epsilon times L, except L has nothing to do with the thickness of the slab. L has to do with optical depth 1 layer. So what does that really mean? That means you have this layer tau equal to 1. Everything behind that layer gets so heavily absorbed that you don't see it. And this layer of optical depth 1 is what you see because it doesn't get absorbed much. So that is the sort of qualitative or English-based description of what is happening in this equation. But the equation gives you this answer. Okay. So I will simply say this is equal to emission from a layer of tau of the order of 1. So this is a thumb rule which astrophysicists have. You look at the sun in some wavelength. Are you looking at the center of the sun? You're not. So depending on what wavelength you're looking at the layer of optical depth 1. It's the properties of that layer which you are measuring. And sun is a good example because for most of the visible region and so on, you are pretty much looking at the same layer. And that's what we call the surface of the sun or the photosphere. So one of the first surprises I got when I joined the Raman Institute was there were people working at the Gauri Vidyanur Radio Observatory. And in fact, Dwarkanath began his radio astronomy career there. And they told me the size of the sun is 2 degrees. I said, come on, the size of the sun is half a degree. They said, no, when you observe it at 10 megahertz, the absorption at 10 megahertz is something quite different, right? So there's an outer layer of the sun which is transparent at visible thing. So you look through it. But when you observe at 10 megahertz, right? No, sorry, not 10. That's wrong. 10 meters, right? 30 megahertz. Then you see a sun which is bigger than your normal sun because you're looking at the outer layers, the corona and so on. So this is something that you guys will appreciate better when you visit Gauri Vidyanur. And a lot of studies of this, of the sun are done by the Indian Institute of Astrophysics. And they very kindly agreed to sponsor a visit. Right? So this is a transparency or slide well worth looking at, okay? Because it just tells you what's going on. Of course, by the way, the real physics is still hidden in this epsilon and alpha, right? And that's what we are going to come to next. But at least we know. And please remember, these also depend on frequency. Just like the example I gave you of the sun looking completely different at visible wavelengths and also at long meter wavelengths, 10 meters. Okay, so I'm going to save this. Maybe before I clear it, I should take any questions. This is the only derivation in this talk.
Sir, there is a question by Aruna.
Yeah.
Is it possible to measure the energy emission in the case of a large distance when the solid angle becomes very small to measure?
It really depends on your instrument. Okay. So, as I told you, one of the smallest astrophysical objects is a black hole, right? So one of the historic achievements of radio astronomy, which took place only 3 or 4 years ago, was to measure, and actually when I say measure, I mean resolve. see, if it's one thing to measure the total emission from some region, then your radio telescope beam, that is the angle from which it collects the radiation, can be much bigger than the object, but you will collect all the radiation from that object. Okay. However, in this case, you actually wanted to make a picture. So many of you might have seen the picture of this ring around the black hole in M87, which was published 2019, I think, and better pictures have come out now. So in that case, they actually had to make a radio telescope whose angle, this is a very far away object, by the way, and it subtends a very small angle, which is measured in micro arc seconds. By the way, so I should remind you, we had radians. Then you have microradian. So arc second is 5 times 10 minus 6 radians. So arc second is 5 microradians. And now you're talking micro arc seconds. So you're talking of 10 minus 12 radians. So the size of this object was some 40 micro arc seconds, and people could make a picture of it. So it all depends on your instrumental capability. So that's the answer.
Thank you, sir. Okay, we don't have any more doubts.
Yeah, great.
If there's any doubt, you can.
No, there's plenty of opportunity for that. We are only at
Yeah.
the halfway mark, I think. Right? So now I want to go back and tell you the deeper significance of this quantity I. So in the case of I knew we took the energy received, right? And then we divided it by so many things. We divided it obviously by time. We divided by the frequency range. By the way, better get used to the radio astronomers' jargon, which is also the cell phone people's jargon, bandwidth, right? And we divided by area, and we divided by solid angle. Now, this quantity actually has a very nice physical significance, okay? And I'd like to talk about that now. So, in fact, it's a natural continuation of what we were talking about. We said that you need to have a resolving power, right? So any real instrument will have some resolving power in terms of solid angle. It will have delta omega min. It will also have a delta nu min. Okay. Now, so this is what we would like to understand. Okay. So let's first look at this delta omega min. So this is related to what we would call angular resolution. So there's a very famous formula, and okay, let me draw the telescope horizontally, looking sideways. So what the telescope does is you have some source, let's say, on the axis of the telescope, and it's really far away. So the wave which comes from the source, the radio wave, is a plane wave when it hits the mirror. But of course, the job of this mirror is to focus it, right? So basically, all the points on this plane are collected. And one interesting property of telescopes is all these path lengths are actually equal. May not be very obvious, but in fact, the parabolic mirror is so chosen that all these path lengths are equal. So basically, it combines the entire radiation received from the source over the aperture of the telescope in phase, because equal distances at this. So that's how you get a maximum intensity. That's how you get a focal spot. By the way, the same is true even of an ordinary magnifying glass. If you burn a piece of paper on it, that's what it's doing. It's collecting the radiation and bringing it to a focus and making sure that the radiation is all in phase at the focus. All right. But what we really want to understand is if I move the source away by some angle delta theta min, at some point, the radiation which I collect here will keep falling, right? Because the waves which are now combined here will no longer be in phase. Now, of course, they may still be in phase somewhere else in this plane. But then you will say that's a different source, right? You have something like a camera or something here. Or even for the radio telescope, you can have multiple detectors, right? Nowadays, this is, anyway, since we are talking radio astronomy, let me introduce some term. This is called an array field, and modern telescopes do have that, right? So what we really are asking is, how far do I have to move the source so that the signal in one of these elements falls down? And the simple answer is when the phase is no longer constant over this plane, but it changes by a significant amount. Now you can worry about what is significant. Is it pi? Is it 2 pi? I'm not going to worry about that in this lecture. The reason is that to do it properly with the mathematics, you need a little bit of theory, which is the theory of Fourier integrals or Fourier series. And one of the things we recommend to all of you is to catch up, revise that theory. And certainly it'll make life very comfortable for me and also for you. If when we meet again on, I think March 1st, you have sort of revised all this, and our friends in Nakshatra have promised to give you some help, and I too can help you, right? So no Fourier theory right now. We're going to make a very simple-minded statement that this is a plane wave arriving from the source, which is on the axis. This is the plane wave which is arriving from a source, which is delta theta min away from that. And if this phase difference, well, let me just call it a path difference of lambda. So phase difference of 2 pi. So this is the diameter of the telescope, right? Sorry, it's the diameter of the telescope. And so this figure is meant to convince you that delta theta min is nothing but lambda by d. So this is another famous formula of astronomy which everyone should know. If you want better angular resolution, you have to go to a shorter wavelength, or you have to go to a larger diameter, or both. In fact, the lectures which I will be giving, not this introductory lecture, but the ones which are more oriented toward the project, will go deeper into this whole idea of what is the resolution of a radio telescope, how can you make this image, right, and so on. And of course, if you actually want to make the image, then really the right person is Dwarka. Right? And of course, if you want to know how the telescope actually works in terms of hardware, the right person is Ramesh. So I'm sort of sitting somewhere in between them. Okay. So this is lambda by d. Delta theta min is lambda by d. Just remember that. So maybe we'll just convert this formula into a delta omega min. Very simple, just square it. In radians, you just have to square it. Well, strictly speaking, you might have to put some pi by 4 or something, because, right, suppose the beam is circular and this is the minimum theta, then the solid area is not exactly going to be theta squared. But as I said, I'm not worrying about those finer details. So delta omega is really lambda over d whole squared. So just remember that. Now, what is delta nu? Delta nu is your ability to distinguish two frequencies. Now, there are many, many methods of measuring frequency in astronomy. But in radio astronomy, what is done is very simple. At least nowadays, in modern radio telescopes, right? You actually have the signal coming in and it's recorded, it's put into a computer. So suppose you're looking at a total time of t. And again, if those of you who are familiar with Fourier transform will know, all you have to do is to take these numbers, push it through a Fourier transform, and then you will get different frequency components, right? And what we're really asking is, what is the separation of these two frequency components? Now, in this introductory lecture, I don't want to bother you with Fourier transforms. So I'm going to make a much simpler statement, which is similar to the statement which you made for measuring the angle of a source, the position of a source in the sky, right? So similarly, I would say you are measuring for a time t, and you want to know what is some delta nu min. Now I'm going to say that suppose you have something which makes a certain number of cycles within this at some frequency. If I shift the frequency, it will make a different number of cycles, right? And in fact, in Fourier theory, you deliberately pick those frequencies which make n cycles, n plus 1 cycles, so on. So I'm going to say that delta nu min is that shift in frequency. And what is the number of cycles? Number of cycles is just nu into t, right? I hope that's okay, right? Frequency nu is cycles per second, and you multiply it by t, give you the number of cycles. So delta tu min into t, I'm going to say, let's put it equal to 1. And this will tell you the frequency, the smallest frequency which you can measure. So this defines the resolution limits. So now you notice something interesting, right? The resolution limit in solid angle is what? Is inversely related to the area, right? So I could even write this as lambda squared divided by the area. And the resolution limit in frequency is inversely related to the time of observation. Of course, you may not want this so much resolution in frequency, right? If you observe even for 1 second, what this formula tells you is that you will have a frequency resolution of 1 hertz. Now, if you're receiving a band of several gigahertz, you may not want to study each 1 hertz in it because your source itself may not have properties which vary on such a fine scale. Okay. By the way, small digression. This is true for natural sources. The people who search for extraterrestrial intelligence would like to use very, very narrow frequency bands because they're assuming that the people or whatever are using devices similar to us. And if you look at our devices, man-made devices like radar or mobile phones, they can radiate in very, very narrow frequency bands. Huh? But let's forget that search for extraterrestrial intelligence and just use. So as I said, this is the minimum delta nu is possible. So just, I'd like you to just remember the minimum solid angle, lambda squared over A, and the minimum frequency 1 over T. Okay. So now we're going to save this and please start preparing your questions. I'm really so happy to have an audience which asks questions. Unfortunately, it doesn't always happen. What did I do? Oh, I saved it in the wrong name. Which means I probably killed the previous one, is it? So what should we call this? We should call it right. So before I erase this, can I take any question on this?
Hello, sir.
Yes.
Sir, if we consider a wave and if we consider the Fourier form of it, Fourier transform of it, so we will get different frequencies for those each for that particular wave. So
yes.
Are we taking the delta nu min as the difference of those two different frequencies?
The two adjacent frequencies.
Yes, sir. So the minimum one I will take as delta nu.
Yeah. So you have obviously studied Fourier theory.
Yes,
but
sir.
As I said, I also gave a simple-minded argument saying that just as in the case of a telescope, we are able to distinguish two directions which cause a phase difference of lambda across the telescope. So I'm similarly saying we can distinguish two frequencies which cause a difference of 1 cycle during the time of observation. But I agree with you and that these qualitative ideas, which will really become very quantitative when we do a little bit of Fourier theory.
Okay, sir. Got it. Thank you.
Okay.
Viren, you can unmute and ask a question.
Yeah.
No, I had doubt in the similar things. I think that answered my question. Yeah.
Can I continue or I did hear someone say something.
Yes, sir. You can continue, sir.
Okay, great. So let's just look at these formulae for resolution. So because I didn't carefully keep track of factors of 2 pi and so on, I'm just going to say this is of the order of 1. Could be. And yeah, square of the wavelength. So now this quantity which occurs in the denominator of I nu acquires an interesting meaning. So I nu is whatever energy you have collected, right? So maybe I'll just call that some delta E. And then it gets divided by all these products. So let's say you've observed for a time. Delta omega, solid angle, area, frequency, interval. See, this is not delta nu min, okay? And observing time. So this product, which is sitting in the denominator, so the A and T are the same as in this formula. You're collecting over a certain area of the telescope and you are observing for a certain time. But you may observe, for a different delta omega or for a different delta nu, right? So then, suppose we, instead of looking at I nu, suppose we look at, let's see, lambda squared I nu. So I'm going to put a lambda squared here. So now this quantity is what we are going to talk about, but we'll turn it upside down first. It's delta omega A delta nu T. And we have a lambda squared in the denominator. Right? Now, A by lambda squared, so this delta omega is there. And what is A by lambda squared? It's the reciprocal of delta omega minimum. And then we have delta nu, whatever frequency band we have decided to observe. And this T can be written as delta nu minimum. Right? So the meaning of this quantity which is occurring in the denominator, after, of course, we have to take I nu and multiply it by lambda squared. Right? So this quantity is actually the number of resolution elements which you have. Right? You are looking at collecting from some delta omega and some delta. And these are the minimum value allowed, right, by the resolving power. So this is the now I can state this in another way. So suppose we make a map at the maximum possible resolution in frequency as well as in angle. Right? Then for each one of these resolution elements, we'll write down some number saying that's the energy we received in that resolution element, either delta, that little minimum delta omega or minimum delta. So this is also the number of numbers in the map. Right? Now this is an idea which we have to think about. Right? So this quantity, right? Just this quantity that we are talking about. the denominator. So the denominator I'm going to call, but I'll tell you what it's technically called. It's called the number of radiation modes. Now this is not, so I don't mind spending quite a bit of time on this because it's not such an easy idea. And so let me state this in another way. Suppose I ask how many numbers, I have some electromagnetic field falling on my telescope. I want to describe it to some other person. I record it. How many numbers should I give that person? You could also call it number of degrees of freedom if you like, because that's what we often talk about in problems in mechanics, right? You say Earth is going around the sun or the planet is going around the sun. So if I want to describe it, what should I do? I should give 3 position coordinates. I should give 3 velocity components. So it has those 6 numbers. Right? So similar statement about electromagnetic field. There's some electromagnetic field. How many numbers should I give? Now, it's a field, remember. There's a different number at every point in space. And the number of points in space is infinite. Right? So really a field has infinite degrees of freedom. However, if you restrict yourself to a given time and total time, that immediately means that the number of frequency components you need is not infinite. Likewise, if you restrict yourself to a solid angle, it means the number of directions you have to talk about is not infinite. The number of directions you have to observe is only delta omega divided by delta omega min, right? So when you observe the sky at a finite angular resolution and a finite frequency resolution, and that is always true, right? No astronomer has the luxury of having infinite area and infinite observing time, right? So your resolution is always finite. Then this is really the number of numbers you need to describe the radiation field which is coming in. So what is conveniently said is each one of these is called a radiation mode. And this concept takes a lot of English to describe, but very little mathematics. So as Rupam told us, if you give me this electric field as a function of position and as a function of time, and of course, it's important that the position is not infinite. It's confined to some area. Time is also confined to some area. Then we can use a Fourier transform and describe it by a finite number of components. And this is just the number of components. So this is radiation modes. Now, this does not only have a mathematical significance, it also has a physical significance. But we'll come to that in a minute. So, I nu itself, let me remind you what the dimensions are of I nu. It is simply energy per unit area, right? Because this quantity is dimensionless, right? It's just the number of radiation modes. And the fact that it's dimensionless came out when we rewrote it this way. Delta omega divided by delta omega min, delta nu by delta nu min. So this is dimensionless. And it's the number of radiation modes. So I nu itself has, okay, so if we go back to I nu, it has the dimensions of energy, right? And then you have area, of course. Then you have time, but you also have frequency. So those 2 dimensions cancel, right? So I nu has the dimensions and solid angle has no dimensions. That's also. So that's why lambda squared I nu simply has the dimensions of energy, right? Which is this delta E, but it's energy per mode. So that's the crucial point. So lambda squared I nu. Now let me give you a more familiar analogy, which will make you see electromagnetic field fills is a wave. It's a wave in 3-dimensional space. But all of you are familiar with musical instruments which have a string. It's a wave in 1 dimension. So here we all know what are the modes, right? This is the fundamental mode. Then this is the next mode, right? So you have an integer number of half wavelength in the string. So when we talk of modes of the radiation field, we're really saying the same thing, right? The electromagnetic field in a given region of space and for a given duration of time can oscillate, and you can describe it as a superposition of modes, just as you describe the vibrations of a string as a superposition of different frequencies. So if you like, radio astronomy has this beautiful musical instrument, which is the electromagnetic field, right? And you receive many, many modes at the same time. And therefore, it's quite interesting to concentrate on the energy per each mode. So now this is what I'm going to talk about. This is an idea which sometimes is not mentioned even in advanced physics courses, but it's a very useful idea. And we also came to it naturally, right? We defined a specific intensity, and we saw two properties of it. One is that it's independent of distance, and therefore it depends on the source. And then we learned how it's connected to the emission and absorption properties of the source. So now I have connected specific intensity to the energy per radiation mode. And I have a reason for doing this, which will become clear. So right now I'm going to save this file. Sorry, spelling.
Sir, in the equality, what you've written, delta omega A by lambda square delta nu T. The next step you have written delta omega by delta min equals to delta nu.
Oh, no, it's not equal to, it's multiplied by. So sorry.
Okay. Yeah. And there are few questions. Yuvraj is asking, is A in delta omega minimum an approximation of the area of the sphere?
Which
Probably the second equation which you have written.
No, which is the equation you're talking about? This equation?
Yuvraj, can you unmute and ask your question?
Yeah, sir. It's the exact same equation.
Well, I think what you're saying is interesting. What it tells you is that if you want an antenna to cover the entire sphere, delta omega min, then the antenna has to be quite small. It has to have a size of lambda square. So if you want to make, now I'm getting a little bit into antennas, but one of the simplest things which many of you see nowadays, you don't have TV antennas, right? It comes over cable. So some of you might be old enough to remember TV antennas, which used to be on top of everyone's house and point toward the local television station. And they basically were hunks of metal like this, no? Some complicated. And they were quite small. I mean, they were comparable to the wavelength. So the connection with the area of this, with the solid angle of the sphere is the following. But most antennas are much bigger than the wavelength, right? And therefore, and that's desirable because, in fact, the biggest single antenna used for radio astronomy is 500 meters in size. It's called FAST. It's called 500 meter aperture telescope, something like that. It's located in China. It overtook the previous one, which was located in the United States, which was only 300 meters in size, for two reasons. One, it was bigger. And the second, many of you might remember, you might have seen in the news that this telescope, which remained the biggest antenna for nearly 50 years, actually collapsed. The mechanical structure gave way. I mean, not because it was badly constructed, it's just age. Okay, right. So yes, this inverse relationship is good to keep in mind, and that's why astronomers keep trying to increase A. In fact, we have not really talked of the theme of interferometry, but interferometry is when you use a large number of telescopes to build up this A. So individual telescopes are small, but somehow they behave like a telescope with a large A, and that will be the theme of what I will tell you, and very much the theme of what Dwarkanath will also be guiding this project. Okay.
Thank you.
Yeah.
Sir, there is another question by Shashwat.
Yeah, sure.
At the start, you wrote specific intensity in terms of frequency and N cap. We also write in terms of, can we also write in terms of position R, frequency nu, as well as n cap, where R is the position of the same electron or photon.
R is the position of the telescope, sir.
He says R is the position of electron or photon.
No. 1 minute. Yeah, let's talk about that. Okay, and then for this question, I don't need this. I'll use just this blackboard. Yeah. See, the first of all, we are talking of photons, right? We're talking of electromagnetic waves, which can be described in terms of photons, right? But ultimately, it's detected at your telescope. So the position of the photon after the experiment is over, first of all, the photon is destroyed, right? It's converted to something else, some electrical signal, and goes to your computer and so on. So I would not put the position of the photon. What this n hat is the direction of the photon. Yeah. So the question is, I is a function of frequency and a function of n hat. And this is basically what we call a map of the sky.
Okay.
And now I
Is
can
it
add one
clear,
more
Shashwat?
statement. Yes.
Oh, yes, sir. Continue. Sorry.
Yeah. So that's it. Okay.
We have another question by Yuvraj.
Yeah. Sure.
Even if the radio emissions consists of various frequency range, when we consider the concept of modes, only discrete frequency ranges are considered. Do we lose some information by this?
Yes. So the concept of modes reminds us that if an observation is made on radiation in a finite region of space and for a finite time, then there is a limitation. Okay, I think that brings me nicely to the next topic, maybe the last topic, given the time we have. It'll maybe also give you a deeper understanding of the concept of resolution and the concept of modes. Now, for this, let me also reconcile these two. I've sometimes used the word radio waves, sometimes we've used the word photons. So is it that all physicists and astronomers have to develop split personalities? And the answer is no. The accurate description of electromagnetic waves is by photons. Okay, no question. Any wavelength, doesn't matter. However, in limiting case of radio waves, the number of photons is so large and the energy of the objects is so continuous that it's an unnecessary luxury to talk in terms of photons. It's easier to talk in terms of waves, electromagnetic fields. But the rigorous thing is photons. Okay. So now what I'm going to do is I'm going to re-express our resolution in terms of photons, and then you will see it becomes something quite interesting. So let's say we have something coming along the axis of the telescope. And instead of saying that it has a frequency nu, let me say it has a momentum p, which is h nu over c. So this is the source which is on the axis of the telescope, which is giving you a maximum signal at the telescope. Then let's put another source at theta min. So how do these two differ? The transverse component of the momentum, right, perpendicular to this axis of the telescope, right? So P perpendicular, it's a small thing because delta is the same as P into this delta theta min, right? Now, so instead of saying I'm measuring the direction of arrival of the photon, I could say I'm measuring the transverse momentum of the photon. Same thing. Now, what is this P delta min? It's h nu over c. And what is delta theta min? Was lambda over d. Now, if you remember your basic, all this cancels. Right? So it's just h over d. Or better still, d times delta p perpendicular is, and remember my calculations are not that accurate, so I'm going to put this wiggly sign, Planck's constant. So does this remind you of something?
Uncertainty principle.
Exactly, right. So whatever we've been talking about modes, so you were saying there's a limitation to our ability to measure direction, and so this is the uncertainty principle for the transverse position and the transverse moment. Yeah. And then similarly, if you look at this thing, delta nu min is equal to the total time over which you observe, the inverse of that. Instead of that, you multiply both sides by Planck's constant, and then you move the delta t to the other side, you will get this equation, delta E times delta t is of the order of Planck's constant. Okay. So, by the way, these relationships are really consequences of Fourier theory. When you express them in terms of direction and solid angle, and in terms of frequency. However, if you decide to express in terms of energy and momentum of photons, they get related to the uncertainty principle. Right? So I hope this is, so in a way you can think of each of these modes as occupying some region of momentum and some region of energy, which is the minimum allowed by the uncertainty principle, or the minimum allowed by Fourier transforms, which is the same thing. Yeah. Okay.
Viren has a doubt. Viren, you can unmute and ask.
Sure.
Hello,
Yeah.
am I audible?
Yeah.
Yeah. As we are discussing about intensity, would it not be incomplete without talking about, now we know that we are talking about electromagnetic fields, and the intensity would also depend on how many polarization states are available for that particular wave, right?
You said how many coherent states are available?
Polarization of the.
You're right. I have ignored polarization. So everything I told you, so if you go to the focus of a radio telescope, simple kind of radio telescope, you will actually see one pair of metal things like this, another pair of metal things like this. And these two are connected to one cable, and these two are connected to another cable. So you're right. The way I have drawn it, you are looking along the direction which the electromagnetic wave is propagating. So I'll draw another figure. This is a plane wave, and this is the direction of propagation. And you have two components of the electric field. I call this Z. I still have an X component and a Y component. And I have just so far talked about the electric field, but really there are two electric fields, Ex, Ey. By the way, polarization is a favorite subject of mine. But even in the 3 lectures that I give, I may not say much about polarization. But certainly one of the projects I was planning to offer does involve polarization. And polarization, for example, the synchrotron radiation that you heard about from Dwarkanath is actually polarized, because you have a magnetic field like this, electrons are moving like that. So the acceleration of the electrons is in this plane, and the electric field you see is also in the same direction as the acceleration. So by measuring the polarization of radio waves and going at 90 degrees to it, you will get the direction of the magnetic field. And this was actually done for this black hole that I was telling you about very, very recently, 2021. So yes, polarization is important.
So it would be in the radiation modes only, is it? The number of
yeah. So so I have done everything not with great accuracy. So the number of radiation modes, whatever formula I had for that, which is actually quite an accurate formula, should be multiplied by 2, 1 for each polarization. Now, of course, you may ask, what is the polarization of photons? So that it turns out it's connected to the angular momentum of photons. So just like electrons, photons have some spin, and the 2 polarizations of a photon, what are called circular polarizations, can be angular momentum. So if you want me to draw a picture, you can have the photon propagating like this and having angular momentum pointing along the direction of propagation, or it can have angular momentum in the opposite. So one of them is called left-hand polarized and the other one is called right-hand. But I'm saying all this not because it's essential to this lecture, but since you raised the topic, rather, I don't think I should start a new topic in the last 5 minutes, right? And well, okay, let me just try, because it's such a simple idea. What is this epsilon by alpha? I have to tell you that. Right? I mean, there's something that played a very important role. The I, which emerges from an optically thick body, is epsilon by alpha. Now, what's the connection between emission and absorption? Now, okay, I think, I hope people don't mind, I'll overspill by about 5 minutes. Now, the first man to think about this was Kirchhoff. And he actually came up with a very beautiful idea. He said, just consider two metal plates at the same temperature. They could be different, need not even be metal. They could have different properties and so on. So each plate has something called E, which is the emission, at some frequency. Okay. So this is plate number 1, plate number 2. So plate number 1 emits E1 and it gets absorbed by plate number 2. So that is A2. So A2 is E1 has some dimensions, energy per unit time, per unit frequency interval. A2 has no dimensions. It's just a fraction, right? So E1 times A2 is the amount of energy being transmitted this way. E1 times A2. But similarly, this guy is emitting E2 and it's being absorbed by the first one, which is A1. So all that is fine. But suppose these are two bodies at the same temperature. Now they need not look the same, right? If you heat up a black piece of carbon or a shiny metal, the radiation coming out of them would be very different, right? However, at the same temperature, you can't have a net transfer of energy from one body to the other. You know, that would make Kirchhoff very unhappy, right? If two bodies at the same temperature, the energy sent by number 1 to number 2 must be the same as the energy returned by number 2 to number 1. So these two are equal, and therefore E1 by A1 equals E2 by A2. So this is a truly brilliant argument. But at T1 equal to T2. So, however, then he took another step. If you carefully prepare this body, what's the maximum value that A1 can have? A1 max is equal to 1. That means whatever falls on it, it absorbs. So this body is called a black body. So this is equal to EBB divided by 1. Right? So the Kirchhoff's law says that for a body at temperature T, the ratio of emission to absorption defined in this way, which is slightly different from our epsilon and alpha. Because those were defined per unit thickness, and this is just defined for the surface. Okay? The ratio of emission to absorption is the same as the emission of a black body at that temperature. Now, how do you make a black body? That's quite a clever thing, which all the experimenters did in the 19th century. They took a body like this and with a small hole, and then they heated it up. Okay? Whatever. Now, if radiation gets in, this surface may not be may not have A1 equal to 1. So it may reflect some of it, right? It may again get reflected. But by the time it bounces around enough times, it will surely get absorbed. So a good approximation to a black body is made by what is called a cavity with a small hole. And since the major experimenters were all in Germany, we still today sometimes use the German word for it, which is Hohlraum. But it's a black body. In fact, in German, black body radiation is called, if you ever read a German textbook, if you read Max Planck on black bodies, you will see this. Okay. So the black body is very important. And now we saw that the epsilon and alpha, if you have a body with tau much greater than 1, what comes out is epsilon by alpha. And this, by the same Kirchhoff argument, this is the same as the epsilon of a black body. Epsilon by alpha of a black body. Right? And that is the curve which you saw in Dr. Armstrong, right? Rising like this. So that is what is called thermal radiation. So I thought I would fill in this small gap. This is studied by people in physics courses. But I think the nice thing about this group is that it doesn't consist only of physicists. right? It has a lot of people from an engineering background. And of course, many of the concepts will be more familiar to engineers than to physicists. Concepts relating to antennas, signals, Fourier transforms, and so on, which we will get to in when I meet you next for 3 sessions in March. So I'm done with whatever I wanted to transmit, but I can receive. So let me, just for completeness, see this. So by the way, I can share with the students. I think Sagar has already seen that mail from Dwarkanath to the group saying that he was very happy that he had to use only 8 slides because there were enough interruptions and lots of questions. So I should go back to him and say I did better because I had only 7 slides and I had enough questions and enough discussion. Okay. Now this is not the end. This is the beginning. But for the purpose of the projects, this plus whatever I tell you, and of course what you hear from the others will be enough. That doesn't mean you can't go further. But those references and so on, we will pass on to you through this learning management system. And I think since before these concepts evaporate, I should, both from my mind and from yours, I will put down a kind of worksheet where you can actually put in numbers and so on. And you will appreciate these things a little better. Yeah.
Sir, there is one question.
Yeah, sure.
Maybe it's slightly off topic, but still I like to ask it. So the question is, just a minute.
Yeah, from whom?
So it is regarding the speed of light actually.
Yeah.
On speed of light that we have measured till now is under the idea of 2-directional way. That is, if you want to measure the speed of light between any two, like if you want to measure, we'll just like switch on the light, it goes to a wall, reflects back, we'll measure the time interval and the distance we know. That's how we can measure the speed of light experimentally. This is a 2-way measurement of speed of light, like it's going in one direction and coming back. So can one-directional is a one-directional way of measuring the speed of light possible?
Yeah.
So
it's
this
possible.
was asked by one of the,
it's definitely possible.
members.
And I can give you another example from the recent history of physics. This is not for the speed of light, but the speed of neutrinos, which were believed, very high energy neutrinos, believed to travel at the same speed of light. So these neutrinos were actually produced in a laboratory in Switzerland called CERN. Okay. And they were detected in a detector somewhere in Italy in a mine. Now, what is then needed is that the clocks at these 2 places must be properly synchronized to that accuracy. So let us say light travels 1,000 kilometers. It only takes 3 milliseconds to do that, right? If I remember my division correctly. So but today clock can be synchronized to nanoseconds. Okay. I mean, with some difficulty with GPS and so on, can be synchronized. So you could measure the speed of light as a one-way thing. And by the way, it was measured for the neutrinos. And initially, when the neutrino result was published, it was slightly greater than the speed of light, and people got really worried. Okay, and therefore the experimenters had to go back and check everything. And somewhere they found that there was one cable in the electronic setup in CERN of some 60 meters or something, which they had somehow missed out on. And when they put in the effect of that cable, they got exactly the same speed. So one way, there is no fundamental difficulty, provided you can synchronize clocks. Now, synchronization of clocks is, of course, a beautiful subject in itself.
Yes, sir. Yeah. And Viren has raised his hand. Viren, do you have any questions you can ask?
Yeah.
Yeah. Hello, sir.
Yeah.
Actually, my doubt would be a bit naive, but in your first slide, you showed that when we were discussing about tau and we were actually having one source which was emitting, and we had dx amounts of layers which were absorbing, right?
Yeah.
And in the end, we said that if the tau was of such a kind that it was optically thick, then we would observe only the last layer which was there. But I mean, how would we know that that was not the source in the first place? Like,
it is. So actually, we don't know. So when you
Yes,
have an optically thick source, you are really seeing only the surface, and therefore you don't know the optical depth, and you don't know what is happening inside. So your question is not naive at all. So you look at the surface of the sun, you see all this electromagnetic, visible light and so on, but you do not see the gamma rays which are produced in the nuclear reactions at the center of the sun. You simply don't see that because they get absorbed. The energy is converted to a lower energy. There is a longer wavelength. So you're completely right. An optically thick object hides all the information behind it.
No, sir. But then the question would be that how do we know if it's optically thick at all? Like, because now we are implying that there are certain layers. If we are implying it's optically thick, we would imply that there are certain layers behind, in between the source, the actual source that we are pointing at. But then we come to a conclusion that there is no source at all.
Okay, let me give you an answer in the case of the sun. At least there I kind of can tell you. Of course, a little bit of theory input is also there, that the inside is hotter and the inside is also denser. And the density keeps coming down, the temperature also keeps coming down. So then when you actually look at the spectrum of the sun, you don't really see a black body spectrum. If you saw a perfect black body spectrum, then all that you will see is that famous curve, and it will give you no information except the temperature. Okay, nothing else you would know. However, this black body spectrum is crossed by thin absorption lines. So that's another layer, a light atmosphere on top of the sun. Okay, and these are actually absorption lines because it's cooler. So I didn't come to that, but a cooler layer will absorb and a hotter layer will emit. So by seeing, if you measure at various wavelengths, looking at absorption, emission, and so on, you can build up a picture of the different layers. Otherwise, I agree with you. If you just observe at one frequency, you cannot. Yeah, so this is really getting into astrophysics. I think there's an astrophysics program also going on at the same time in Nakshatra. I don't know if they are discussing all this. I'm happy to talk about it. And answer to Bhuvan Bagwe's question is yes. The actual radiation which is detected from the black hole had a wavelength of 1.3 millimeters, okay, or a frequency of 230 gigahertz. But for display purposes, that intensity was converted to colors, so false color. Yes.
Okay, sir. There is another question by Bhuvan. He's asking, was the image of the black hole a false color image?
I already answered that because I saw it in the chat.
Oh, okay. I think there is no more questions unless anyone wants to unmute and ask.
But by the way, if you think of some question later, I think you can put it in the learning management system, or if you're not completely used to that, send it to Sagar, who will pass it on to me. But gradually,
yes, sir. And in LMS, we have a tab open for learning. I mean, in the open discussion, there's a chat room open.
Yeah.
Anyone can go and put your questions there, and sir can view the questions. Or there's also something called as open discussion or in a forum.
Discussion forum.
A general forum, discussion forum. You can put your questions there.
So maybe I will open a discussion forum for my lectures so that if people want to ask, they can post there. Otherwise, I have to go to the chat room. But chat room can be for the whole group, no? I don't know. How should we do it? You tell me what your experience.
What we can do is we can create a forum named like in your name. We can create a forum.
Right.
And
so any question specifically to me can be put there. And if it's a very general question, maybe why don't you check with the other instructors also? And if everyone is fine with that, let's do it. Only thing is we have to get into the habit of checking that. That's okay.
Yes, sir.
Unless sometimes Moodle will even send you a reminder. I don't know whether